Welcome to The Explainer. Today, we're doing something really cool. We're going to take a simple list of numbers from a science experiment, plug them into a basic spreadsheet, and watch as a fundamental law of nature just appears.
So how is that even possible, right? A spreadsheet uncovering a law of nature. Well, let's dive right in and see how it works. We're going to start at the very beginning, with the raw, messy results straight from a basic gas law experiment.
So, every scientific journey really starts with a puzzle. And in our case, it's this collection of raw measurements that, honestly, at first glance, they just look like a totally random list of numbers. And here it is. This is our starting point. You're looking at the data exactly as it was jotted down in the lab. We've got 3 columns: volume in milliliters, temperature in Celsius, and gas pressure in hectopascals. But right now, it's just a table of numbers. Whatever relationship is hiding in there, whatever story it has to tell, it's completely invisible to us.
Okay, so here's the first crucial step. Before we can find any pattern, we have to translate this data into the universal language of science. Think of it like this. We need to get all our measurements speaking the same language so we can compare them properly. That means we've got to do a few essential conversions. Which brings us right to our next phase, decoding the data. I like to think of this step as us forging the keys that are going to unlock the puzzle inside all those numbers. It is all about the prep work. And it's a pretty clear 3-step process. First up, we're taking volume from milliliters to liters. That's just dividing by 1,000. Simple enough. Second, temperature goes from Celsius to Kelvin, and all you do there is add 273. And finally, we'll convert that pressure from hectopascals to atmospheres. Once we do that, we have our standard, ready-to-use units. Now, you might be wondering, why bother with Kelvin? Why not just stick with Celsius? Well, this is a really big deal. See, Kelvin is an absolute scale. 0 Kelvin means absolute zero. It's the point where all molecular motion literally just stops. And for the kind of gas law math we need to do, using an absolute scale like this is non-negotiable. It's absolutely critical. And here's a great before and after. On the left, you've got those lab units: milliliters, Celsius, hectopascals. Totally fine for jotting things down during an experiment. But on the right, that's our after: liters, Kelvin, and atmospheres. These are the standard units that let scientists everywhere compare results and do some really powerful analysis. Okay, so our units are decoded. We're almost ready. We just need to do 2 final calculations to get the exact values we're going to put on our graph. First, we're going to calculate temperature divided by volume. And second, we'll get the absolute pressure by just adding 1 to our atmosphere value. These 2 new columns of data, these are the keys we've been looking for. All right, this is it. Let's get to the most exciting part, where all this prep work leads to a genuine aha moment. Seriously, this is where the magic happens. The stage is totally set. It is time to see our data. We're just going to make a simple scatter plot. On the vertical y-axis, we'll put that temperature divided by volume number, and on the horizontal x-axis, our absolute pressure. Let's see what happens when we plot them against each other and finally hunt for that hidden story. And wow, just look at that. The second we plot the points and tell the spreadsheet to add a trend line, what was just a random cloud of dots, suddenly, it's like magic. It organizes itself into this clear, almost perfectly straight line. This is that moment of discovery. Okay, but what are we actually looking at here? This isn't just a line on a graph, It's a story. And it's telling us something incredibly profound about how the physical world actually works. So just how good is this line? Well, look at this number here, the R² value. It's 0.9997. Now, in the world of science, a perfect fit would be a 1. So yeah, this is incredibly close. It's screaming at us that our data isn't random at all. It's super consistent, super reliable. There's a real, powerful relationship between these variables. But the real secret, the big discovery, is hiding in the equation for this line. Remember, y is our temperature over volume, and x is the absolute pressure. So what does that mean? It means m, the slope of the line, is the constant that connects them. And this isn't just some random number. That slope we just found is directly tied to a fundamental constant of nature, the ideal gas constant. Okay, so let's zoom out for a second. What's the big picture here? What's the real takeaway from all this? Because it's about way more than just one lab experiment. See, this whole thing wasn't really just about finding the gas constant. It was about seeing the incredible power of visualization in action.
We just watched a simple spreadsheet take a bunch of seemingly chaotic, raw data and turn it into a clear, beautiful, understandable insight that is literally a law of physics. I mean, just think about that for a second. We started with a simple list of numbers, and from that, we revealed a fundamental law of nature. And we did it with a tool that you almost certainly have on your computer right now. That's the power we're talking about in this explainer. The ability to turn data into discovery is more accessible right now than at any other point in human history. And it really makes you wonder, doesn't it? What other secrets, what other patterns and fundamental laws are just hiding in plain sight in the data all around us, just sitting there in a spreadsheet, waiting for someone like you to ask a right question and visualize the answer?